Oh, yeah, now it's fine. Yeah, great. Thanks. So that simple things work. Okay, so here is the plan for today. Okay, so we have some H. And remember, we're talking about binary classification. So we have some set X. Yeah, so we have functions H in X are from X to 0, 1. That's it. Okay. So yeah, it's binary classification. And the thing about H is that it has some structure. So what is the structure? Structure is simply that its growth function is small. So let me just define growth function once again. Growth function of this class. So we say that okay, X is our use set. Okay. So X here is our use set, and possibly infinite. And however, we look at some restriction of H to subsets of X. So let's see the any finite subset. And then we ask that let's just finite of size n. And we want to know that how many different restrictions, how many functions are there in the restriction of H to C. So let me just define restriction once again. So restriction of H to C. So C is some finite subset of some size n. And what is the restriction? So we say that let's look at the number of distinct functions which are induced on C by H. So particular it is XC is the restriction. That's how we the symbol for restriction. What is this? So we say that let's look at all functions in capital H and see what functions are induced on C. So what's a function on C? We are saying that what values do functions from H produce on C? So let's take a function H in H and look at the vector of values it produces on C. So H of C1, H of C2, H of C. Assuming that C has some ordering. So let's say C has some ordering. C1, C2. Okay. And the whole trick here is that two different functions of H can produce the same vector like this. And that is why HC can be much smaller than H. So yeah, just remind you with example again. Let's say H is some step function on the reals. So H is step functions. So H is clearly an infinite plus. It is actually undoubtedly infinite. But now if I pick up small c, suppose c is suppose c has two elements, A and B. Yeah, so let's call them A1 and A2. So you have some A1 here and A2 here. Then how many vectors like this are possible? Anyone for this example? So we have a function like this. So if my H from here looks like this, then the vector is 0, 0. right? So I can get 0, 0. I can get 1, 0, and I can get 1, 1. I had 3 vectors. So XT only has 3 elements for this, even though my H is 25. Right. In particular, yeah. So if you're talking about binary classification, then ST will have, at most 2 to the C elements, because yeah, I mean, for obvious reasons, each of the CIs are either 0, 1, so there are only these many. But the question is that can it be much less than 2 to the C? So if it is very 2 to the C, then you cannot write once again. Yeah, because again, an every function is possible, and by arguments similar to no freelance theorem, you cannot write. Yeah, so the question is that can it be much smaller than 2 to the C? So here you don't have all 4, so 2 to the C is 4, but here you only have 3 guys. So yeah, so how much smaller will it be? Yeah, so and yes, so to capture that, we have the idea of a growth function. So let me just define that. Okay, maybe I can. It is this. So C is this. So what's the growth function? The growth function says that, okay, so it's a function of m of size. So it's a function tau h, yeah, tau script h, and it is from natural numbers to natural numbers. And what does it tell me? So th of m is the maximum size of HC for any C of size n. Okay, so look at all subsets of my ground set X whose size is n, and we ask how big can this HC be? So yeah, that is what tau h is. So for this example, actually tau h of 2 will actually be 5 to 3, because you cannot have more than 3. Tau h of 3, tau h of 2 will be 3. Okay. Yeah, so that's this growth function. And now, what I want to say is that if my growth function does not grow very fast, then I can learn my class H. That's my plan. So we certainly state that, and then we will try to correct everything and improve things. So yes, we have some class, and and let's say I know the growth function tau h of my class. The growth function tau h. Now, I want to say that okay, for every distribution T, and every epsilon delta is in 0. So here the distribution is on X. On X. And for every epsilon delta greater than 0. We have that we can learn our function from X. We can learn any target function. So, so we have that with probability. Actually, I can also define distribution on X and labels. If I want to be in the agnostic case, so I have distribution only on X if I'm in the realizable case. If I'm in the agnostic case, then I have a distribution of x and variables. Certainly similar to the agnostic case, but let me make life difficult. Till now, that has been easy, so sometimes you should have a difficult. So yeah, so now we have some distribution of x and variables. So yeah, so this is a big probability minus delta. You have that. Yeah, you will learn with an error as well. So what does that mean? It means that okay, so with this probability for all estimates, the difference between the true loss and the empirical loss of h is, and then as you know, we will do it. So yeah, LD, right? That is the true expected loss of h under distribution D minus the empirical loss. So I think it's LS. Okay, so there's an empirical loss under sample S. So so if a sample S from distribution D, yeah, some n times. So for all when S is sampled, distribution D, and yeah, and what is M? Yeah, that's a trick. So M is a function of observed. So there exists some M epsilon delta, so that the probability, the high probability, if you sample, if you take M samples from the distribution, then the true loss and the empirical loss will be close. Yeah, so this tells you that you can. Okay, so yeah, okay. Okay, so now of course here you have to, okay, so this is not a routine setup. You have to say what tau h is. Because if tau h is grows extremely fast, so I have to say some condition on tau h. So all of this works as long as tau h satisfies some condition. So what's the condition? So yeah, so to state the condition, I will just replace epsilon with some function of tau h, and then if that function of tau h goes to 0, then it means that I can make epsilon as smaller. So yes, that's what I do. Okay, so this is the definition of learnability. I mean, not a definition, but yeah. So this is what we call the uniform convergence notion of learnability. But I will just now replace epsilon. Actually, you don't have to say this. So yeah, so there will be some function of delta of epsilon and n. So this is in fact at most 1 plus square root of log tau h of 2n divided by delta. Okay, so yeah, so that's the first here. And now you can see why this implies what I wrote earlier. Because if this tau h does not grow very fast, so let's say this tau h is some polynomial. Let's say the tau h is n to the let's say tau is n square. Then what is this? This is roughly n, or maybe this is like square root n. And this square root n cancels with the square root n here. So then this looks like 1 over delta. No, sorry, whatever. Okay, sorry. So this is square root log n. This is square root log n. they have like delta root. So I'm ignoring all constants, ignoring all these 4s and 2s and everything. This is like square root log n because log of n square is like 2 log n. This square root log n is square root n. So now if I want this to be smaller than epsilon, I can easily do that. I can choose m to be pretty big, and this will become smaller than anything like that. Yeah, that's why this is learnable. Okay, good. Yeah, so basically I have to just prove this statement. That will imply that will imply uniform convergence. By the way, in case people are confused about how uniform convergence works, do you want a refresher on that? Maybe I'll do that in case I think people might have forgotten how it works. Okay, so this is here. I hope this is what I have to repeat. I mean, this I can say this. Okay, yeah, this is a few words for uniform convergence, very brief. So we will connect everything and include it. Not lost. Okay, so we say that hypothesis class has uniform convergence. If so if you have that, so if for all d and for all epsilon delta equal 0, there is not epsilon, right? Epsilon is 1. For epsilon delta greater than 0, there is some number of samples I can take, so that so with high probability the true loss and the empirical loss are close for every function. As long as I take S samples, where S is sampled from the. So that's the convergence. It says that if I take enough samples based on epsilon delta, then for every function in my hypothesis class, the true loss and the expected loss, the true loss and the empirical loss from the samples will be as true as well. So that is convergence. And what we showed in previous class is that uniform convergence implies learnability. Uniform convergence implies factor. Yeah, so this we showed earlier, and it is not hard to believe also. I mean, even if you don't remember exactly why, it's easy to believe. Why? Because what's the algorithm? Okay, so what's the algorithm for pattern learning? If you have used it. Yeah. So you just do the most stupid thing possible. Take your samples S and pick the hypothesis which minimizes the empirical loss. And since the actual loss and the empirical loss are very close, minimizing the empirical loss also almost minimizes the actual loss. That's the that's it really. You can write some more algebra to prove it, but yeah, these are the things. Yeah. So this is uniform convergence. And what this statement tells you, is that a class H with a small growth function, so small this thing, will have uniform convergence. Because no matter what my epsilon is, I can just choose my m large enough to make my difference between the true loss and the empirical loss small enough. Yeah, so that's the whole picture. Okay, good. So this is what I want to show. And and why is it useful here? I mean, why should we do such a thing? So we will also show that classes with small mixed dimension have a small growth function. Yeah, that's for the next class, but just to just for a break. So PC dimension of h to d, then tau h of m looks like, yeah, approximately, don't take it very seriously, m to the b. So yeah, so it is polynomial in F. That's the point. So if t is a fixed constant, this is polynomial in F. And again, for the same kind of argument, tau h of 2m, if I take the derivative log, it looks like square root y. So if there is a d there, the d comes out, you have like a root d. You have d, it looks like square root d log n. So this is precise. And yeah, and then if d is a fixed constant, then yeah, then you can just choose m to be as big as you like, so that this becomes smaller than epsilon. So any epsilon that is. Okay, so all of this will then show that classes with finite digit dimension are then the so yeah. So that's the whole picture. Why we do this? Okay, yeah. So but this is for next time. This I want to do it. Today the goal is to prove this. Okay, that's a bit summary. Any questions about any of this? Okay, this is a long proof, so yeah, brace yourself. Try to finish it. Okay, so yeah, so let's begin the proof of this. Here we will have actually just two tricks. The proof itself might look long, but they're really just two ideas. So the first idea will be to get a handle on this difference. So remember, this is the difference between the true expected loss of h on d and the empirical loss of h on the samples, on the n samples which you have drawn. I want to get a handle on this. Yeah, and how do I do that? So remember from previous class, yes, the previous classes, that in general in life, when you want to look at the difference between some random variables expected value and sample average, then it is good to look at concentration. So okay, so you're not a proof yet. This is just giving ideas. Proof will be doing another 3 minutes. So okay, so first idea is to try to use concentration. The concentration should come somewhere. Why? So much concentration appear, intuitively, because because LDH is a true expectation. So LDH is expectation of, so you draw such xy from the distribution. Remember now in agnostics I'm drawing x and y. So I draw sample x and its label y. And I look at the difference between hx and y. Yeah. So let's see how that's why you're different or not. So this is an expectation, and LFX is a sample average of this quantity. So LS of H, remember, is just 1 over m. 1 to m. Indicator of Hx not equal to y. And H of xi not equal to y. So what are xi, y are samples. So S is x1, y1. So this here is the true expectation. This is the sample average, and yeah, and then you want to say some kind of law of large numbers thing, like law of large numbers or center limit theorem. Actually, if I take a lot of samples from the same distribution, right, same distribution T, then the sample average should converge to the yeah, to the two expectation. This should converge. So yeah, and that's really what we're saying here. If we take a lot of samples, yeah, so if we take a lot of samples here, these should get close with high probability. So yeah, so this pattern comes up here. So that's first idea. Somewhere in the group concentration will appear and will appear in this group. Good. Okay. Okay. But now I want to see, okay, how can we make it appear? Like, let's think backwards. Somewhere I have to use this. So yeah, how should I do the proof so that this ends up appearing naturally? Okay. So here is maybe one stupid idea. It's a wrong idea, by the way. So don't take it seriously. It's a wrong idea. It's a wrong idea as a follows. That, okay, suppose I had just one edge. Remember, I have to do this one edge. I want that to high probability. This should happen, for possibly infinite edges. But suppose I had just one edge. Just one edge. If I had just one edge, then I would say that, okay, these two should become close with a very high probability, right? Because of this concentration, because of this, law of large numbers. If I just one edge, then LDH minus LSH should become smaller than some because the epsilon is common. Should become smaller than epsilon with very high chance, with probability. Yeah, so some maybe exponential small probability. The probability is something like, maybe something like n epsilon, maybe something like this. And so you try to get some statement like this, and then say that hey, so this is for one edge here. And then say that, okay, I want to use some kind of union bound. For one edge, it is very small. The probability of, so I wrote the other way around. Okay, so this is bigger than epsilon with a very small probability. So it's smaller than epsilon with a high probability. So bigger than epsilon with a very tiny probability. So what's the chance that there is some edge where things are wrong? Well, I just try to multiply this small probability with the number of edges. But the number of edges here are infinite. Edges should be infinite. But then if you want to say, okay, edge is infinite, but on any subset of size C, it is small. There is only small number of edges. So that's where the growth function should come. So so we have some C of size n. Actually, this dimension is not confused. Okay, so that's what we're going to confuse them, not confuse them. So let's say for now I don't confuse them. Might as well. This is a wrong idea. I'm not giving you the wrong idea. Let's say, I'm looking at my samples. Remember, I have n samples. On those n samples, I know that there are only m to the d. So on those n samples, equal to, let's say I have n samples. On these n samples, there are only tau h of n hypotheses. There are only these many guys, and so I just multiply this by tau h. So on these samples I have only these many guys, and I want this to be smaller than and this I can make smaller than right now. Remember, delta is the probability of a mistake, of a great mistake. So I want this probability of going wrong to be positive right now. And hopefully, if I manipulate this equation, then something like this will come out. I'll get some log here because the e is squared because the 2. So hopefully, I will get something. But as you can see, this is completely wrong. I mean, why can I say do these things? Makes no sense. Okay, but imagine if I could do all this. I could just say that, okay, on my m samples, I have only these many hypotheses. And therefore, I just multiply this small probability by this number of hypotheses. If I could somehow magically do that, I would probably get this. Okay, so yeah, but that's the wrong idea. I can't do that. Fine. So the question is that how do we make this wrong idea right? So I want to make some changes here so that this becomes correct. So the first issue here is that I really talked about the number of hypotheses on the samples which I have drawn. Right? I did average of m where I do these m samples. But that is stupid, right? I mean, there are infinite number of hypotheses. Why can I just look at these m hypotheses? So yeah, so I have to somehow find a way of going from infinite hypotheses to hypotheses only of the samples. I have to find this bridge. If you can find a bridge like that, then I can do this argument. So that's the second idea. That how do I construct that? So idea number one is there's some here in concentration. Idea number two is this bridge construction from H to hypothesis on lines. Okay, so let's see how to build that bridge now. And I will erase this, by the way. Hopefully you can just memorize this. Just remember that it's on the form log tau x by n, square root of that. Just remember. So I erase this. Okay, so let's start building that bridge. Okay, so step 0. Okay, so let me try what we're doing. So the second idea is to go from H to something like H on M samples. Okay, so it's restricted to samples. Yes, so that's idea number 2. And okay, so let's see how to execute this. Okay, so remember what we have to do, we have to look at the difference between LDH and LSH. And I want to somehow go from this difference to difference over these m samples. I have to somehow forget the entire class. Okay, but okay, how are we going to do that? So okay, so step 1 of this. So step 1 is to notice that LDH minus LSH can be written in terms of samples alone. Remember, this is the difference between expectation over a distribution and empirical average over samples. But I don't want to talk about a distribution because, yeah, that's too much. There's too many samples. I want to look at only m samples in my life. I want to forget everything else. I want to forget the whole distribution. So, yeah, I want to somehow go from this difference to difference only over samples. So let's try to do that. So here is what we will show in next 10 minutes. So what we will show is that expectation over S. Okay, so I draw n samples. The can look at the maximum overall hypothesis of LDH minus LS. Remember, this is the quantity we care about. So I have drawn examples, and I asked that how different can the true loss and the empirical loss be over every hypothesis. And I asked the average of this over all samples. So, okay, so by the way, why am I looking at the average? Because in the end, I will use observation. I will say that, okay, if this average is small, if it is smaller than epsilon, then by law of large numbers, with high probability, this will actually be. So, yeah, so generally, if I have some, so expectation is smaller than epsilon, then with probability 1 minus delta. Yeah, the probability, the probability 1 minus delta, x is smaller than. So yeah, something like this. So yeah, so expectation is small means that the high probability the variable itself is small. This won't happen in general, but by law of large numbers, this will happen. For this particular x. So yeah, so that's the idea. And that's why it's enough to just bound in expectation. Because then this computation will take care of what they actually want. What they actually want is some high probability statement, and some computation will take care of it. So yeah, so right now we will just look at the expectation of the maximum possible difference between these two overall H. So yeah, so prove overall H of the difference. How big can this be? So yeah, so we care about this. And remember, I want to somehow get away from looking at the expectation of this overall sample. I want to somehow look at no, okay. So I want to somehow get around this LDH. So LDH is the error over distribution T. I want to somehow look at the error only over samples, so that I can use this wrong idea. So okay, so here is the first line. This is the LDH. Okay, so this expectation is actually a expectation. So over two samples, so S and S prime, both drawn. Yeah, so now I draw two sample sets. Instead of drawing this one sample set of size n, I draw two sample sets of size n. And I look at how different the empirical average is. So yeah, so what have I achieved here? Remember earlier, I was looking at the difference between LS of H and the true average of H over T. I've gone from the true average of H here to a second empirical average of H. Maybe I should draw the line here. Okay, doesn't matter. So yeah, so I replace this LDH by this LS prime H. And this is also, yeah, now I take another M sample to look at it. And now the hope is that because I've done this conversion, I can now maybe just look at the growth function, or in particular, the restriction of my capital H to the set of samples of SS prime. So SS prime has two M samples now. So I have some x1, y1, xn, yn. S, and I have another M samples. Xn prime, Yn prime, Xn prime, Yn prime of S prime. What is this saying? It is saying that let me look at every pair of M samples. Yeah. So there are infinite pairs. And I want to take the average over those infinite pairs. That's his expectation. Weighted average by this distribution T. So I weight T different pairs by distribution T. Yeah, so I have infinite of these N sample pairs. And for every pair, I ask myself, how big can the difference between the empirical averages be? The empirical average losses be? How big can this be for the worst case hypothesis in it? So pretty much more average. Yeah. So and this is an upper bound over what we really wanted, which is the difference between the empirical average and the true average. The con from empirical versus true to empirical versus empirical. And now the hope is that I will be able to just look at the restriction of H to these 2M examples. Because now we only care about these 2M examples here. Now the dependence in this part over the entire distribution is gone. So now we just look at 12 samples and hopefully I can use this gross function. The function over 12 samples is small. That's why there are 2M there. Anyway, it doesn't matter. So that's the plan. And I don't do this by the way, I have to do this. This is frame 1. And now, okay, so from this, how will we proceed? Let's say we can close this and do that 10 minutes. But let's say we have this. By the way, I want to just say, intuitively, why this repeated? Can someone guess? Like, I mean, just intuitively, why this repeated? Why is this something you should do?
So, degree of H is simply expectation of this dash of H. It's just sample from D, and then yes, I simply take this expectation outside by. So for that, I have to first put this. This would be this modular mod of expectation of LSH minus LS dash of H. Then I put the mod inside, so that will give me the first inequality. And
you bring calculation. And just tell me intuitively. So intuitively, what's going on? So okay, so here's an intuition, right? Let's say I have some random variable x. What is this thing? This thing is very roughly, it is expectation of x minus mu. Then mu is the average of this. So some random variable x, which by x I mean, okay, I'm not talking x because there are 2 x's now. Some random variable y, and this thing here is roughly y minus the average of y, the expectation of y. Right? This thing is the expectation of y. So some expectation of y minus b. I'm asking that if I draw a sample from y, what is the average distance of this sample from the average of the expectation of y minus b? So what we are saying is that this expectation should be smaller than if I draw 2 samples. The expectation of y1 minus y2. So yeah, so y is some distribution D. So if I draw y from D, then look at the average distance over D from the mean. This should be bounded by, if I draw 2 samples, y1, y2 from this distribution, and I see how far they are. So this is roughly what's going on. And why should this be true? Okay, so I mean, it will be what's going on, right? So the trick is that, look, if on average uh, a sample from Y is far from the mean, then two samples from Y will be far away. So yeah, so you have some, draw. So if my Y looks like this, it's a very small standard deviation, then two samples from Y will be close. So if I draw two samples from Y will be most likely close to the mean. And indeed, if I draw one sample from Y, it will also be close to the mean. Yeah, there is the other way. I mean, okay. What's more interesting is in that case, right? That's what we care about. So if this is large, then distribution looks like this. So a sample from Y will be far from me because it has this very heavy tail. This sample will be far from the mean. But now, if I draw two samples, Y1, Y2, they will also likely be far away from each other. Because you get one sample from here, likely one sample from maybe here. Because you have a very fat, you have a lot of mass. So these will likely also be far away. So that's all we are saying. If Y is far from the mean, and on average, then two samples from Y will also be far from each other. In English, that's all. You can prove this also mathematically later in science. But
I am not getting why this inequality is building. If there would have been some term like supremum of y1 minus y2.
Oh yeah. This is not an exact proof. I'm just giving you the idea that why should you believe something like this? You should believe this because of this idea. I have not proven this. This is not a proof. Yeah, so the whole thing all this supremum issue. This is supremum here, right? And this is one thing. Here I have supremum over h. So yeah, good. But okay, this is just to give you an issue. Fine. Oh, okay. Yeah, actually, let's prove this. Yeah, I think maybe a little bit, under confidence, let's prove this. So yeah, so we will do now what Ali was trying to say. So okay, so what's the idea? Okay, so let's look at this left-hand side, and yeah, this is just this is just expectation, distribution, supremum x from x over in our idea is the expectation of x prime to the n ls prime x minus ls. So I haven't done anything here. That is the definition of LDH. That's it. Okay, now, okay, now we can take this prediction outside, by the way, because this is a constant. This does not depend on S prime. We'll take it out. This is S prime. And now you can say that
Supremum inside expectation.
yeah, that's the issue.
Because its pointwise maximum. Like if you put the supremum inside, then it will be pointwise maximum. So the maximum of the expectation is less than equal to expectation of the pointwise maximum.
Yeah, exactly. Yeah. That's it, right? Yeah, but I'm just wondering if this is obvious or is it not obvious. I mean, this thing I wrote here. Is it obvious or is it not?
Yeah, this is fine.
The point is that there's an absolute value. Okay, that's the thing.
Yeah, so, this is just triangles inequality, right?
No. Okay. So right now this expectation is only the first guy, right? And okay. So I want to say that I can take the expectation and I can write like something like this. I can take the absolute value inside. Yeah. That's the question. Is it obvious that I can do
So this would be the expectation of given is dash sample from TM of LS dash of H minus LS of H. And I'm taking mod of that. So it's like mod of expectation X is less than expectation.
Yeah, exactly. That's it. Yeah, this is clear. There's no confusion. Okay, yeah. So I suggest taking mod here. Yeah, I'll take it. Maybe I decided, you know, I decided here. So right about that. So I get here. So first I get for sure S prime of L prime minus LH mod. So this is definitely there. Here there are nodes. All I've done is, all I've done is replace LT by this and take expectation here because there is no. They're not right now. And then I just say that, okay, it's mod of prediction of any random variable. So is the most prediction of mod of that. This is almost true. So I get, so therefore I can take this prediction. That and is a mod. So it's mod now goes inside. So mod is now inside. And now we are, and now I'm going to exchange supremum and expectation. And I can also do that. This is true also supremum over, so in general, if I have two random variables, so maps of expectation of x1 x2. So expectation of x1 and expectation of x2 is something is wrong. So
this is the expectation of X X1.
Yeah, exactly. So this goes, especially so this is the most expectation of maps. Correct. This is always true again. And I made you assignment questions in case you haven't heard of that, then you will post it to that. So yeah, these two one is that why is that true? But I just apply this now. So essentially I'm taking maps over random variables produced from different entities. And this says that I can just take the expectation outside and the maps inside. So I can switch to the switch here. At most expectation outside and the maps. I'm not super on the maps. Yeah, so doing this only increases my value. Yeah, so switching expectation and maps like this only increases my value. So I just put an equal to and increase. So I haven't done anything special. I just use these two tricks. You can take absolute value inside and increase the value. You can take maps inside and increase the value. That's all. Great. And now we are done. Because this is actually this is what we wrote, right? Now just combine these two as an S prime and we have a. So we're done. So no, and nothing very mysterious. Everybody remember the idea, right? If random variable is far from the mean, and two samples are also far from each other. have to somehow use the growth function. Let's do that. Okay. For second step, here's what we will do. So let's think about what expedition means. So remember, I'm drawing two sets of M samples. So let's just, instead of thinking, let's just put it on paper. So we're going to use table here. So, so 1, 2, 3, 4. Let's say I have 4. This 4 here. So let's say I'm drawing, two sets of prepared, and then it's 4. So I'm drawing two sets of 4 samples. So 1, 2, 3, 4. 1 prime, 2 prime, 3 prime, 4 prime. So these are my 8 samples which are. So maybe so each row of this table corresponds to some drawing of these 8 samples. So maybe here I do 10, 3, 8, 7, 6, -5, -2, 8, whatever, right? So yeah, I draw here some graph. And there are like infinite rows of this table. So, and now for each row of these 2 samples, I'm asking that what is the maximum of LSH and LS prime H? Or the difference between LS and LS prime H. So I also have with me these hypotheses here. There are also infinite hypotheses here. So let me draw infinite columns. I can't actually draw infinite columns, but just imagine that there are infinite columns. So I have, some H1, H2, H3, and so on. There are infinite columns here. For every column, what will I write here? I will write here the difference between LS on loss, empirical loss on S and empirical loss on S prime. That difference I will write for H1 in this cell. Then when it H2, I ask for hypothesis H2, what is the difference between the empirical loss on S and the empirical loss on S prime? I write the difference. And so on. Write all these differences. Now what do? I take this so. I look at infinite entries. I take the biggest one, and that is my answer. The answer is the max of all these guys. Max of all the numbers. Answer. So for every pair of these M sample, I have an answer, which is the max of these differences. And what is my overall answer? What is this expectation? It is the average of this answer over all the rows of this table. This table has infinite rows. I take the average over the infinite rows. So that's what it is. Now let's try to get a handle on this. Remember, I want to somehow use the fact that for any 8 samples, remember I have 8 samples. For any 8 samples, the number of different hypotheses here is very small. Even though there are infinite columns in this table, the number of different numbers you will get here is very small. There are only towers of 8 many different numbers here. So there are only towers of 8 different numbers. So that fact I want to somehow use. Okay, so great. However, notice that these towers different numbers, different columns, can be different for every row. So maybe for this particular row, the first 8 columns are the different ones. Maybe for this row, the first column and the 10th column and the 100th column and maybe those are different. So which these towers of A guys are, that can depend on them. That makes my life a little complicated. Yeah, fine. Okay, good. But now let's try to build the argument. Let's try to make this long idea work now. So, okay, so let's recall, right? What was this long idea? The idea was that if I had just one edge, if I have just one column here, then this average over all rows will actually be small. Why will it be small? Because large numbers. I am drawing a lot of samples here and a lot of samples here of the same distribution, so they will likely be very, very close. Yeah. So for one edge, I would really be good. The trouble is that same edge does not appear in these different towage 8 samples. So the edge here for this for towage 8 different guys for this stage, for this row, may not be the edges for the towage 8 guys for this row. So if magically they were the same, if this towage 8 different guys were the same magically for all rows, I would actually be done. Right? I would just say that okay, for each of these towage 8 guys, with high probability, the difference there is very small, right? And since I only have towage 8 guys to look at, overall probability is also very small. The overall probability of going wrong is also very small. But the trouble is, that these guys get mismatched across rows. How do we get around the mismatch? Okay. Okay, yeah. So that's the question. How do we get around mismatch? If I can just get around the mismatch, I'm good. Is it a problem? Like, what are we trying to get around? Okay, so now here comes the third trick, third and final trick. You know what tricks? Third and final trick. Third and final trick is saying that okay, fine. There's a mismatch, right? The towage 8 guys are not the same across all rows. And that's why we are in trouble. I can't just use the simple idea that for every edge, the average is small. I can't do that. But what I can do is this. I will identify some subset of these rows for which the towage guy losses. And I say that okay, even for that subset, my average is small. So so what's going on? So let me be more concrete. Let me fix some row here. So let's look at this particular 10, 3, 8, 7, 6 to 180. And now let me identify some subset of rows over which the towage 8 guys will actually all be the same. So it's good. So you have the same different towage 8 hypotheses for all of those rows. But now those will not be infinite rows. There is a finite number of rows. And hopefully there will still be enough of those rows so that the average for any edge is still small. Remember what was the idea? The idea was that for any edge, the average value here is tiny. And so, it's tiny with high probability. And so, over a small number of different guys, the overall average is also small with high probability. Here I relied upon having a lot of those to average over. And that's what log numbers was. Have a lot of those to average over. But now I want to strike a balance. I want to say that I will not work with all the infinite rows because that will give me different towage rates, which makes my life. But I will still have enough rows here so that this averaging over a lot of rows idea still works. So yeah, so let me just maybe put it here. Okay. So what we will do is that so let's fix an SSY. Let's fix this address. Freeze these. And now I will generate S prime pairs such that H restricted to the SS prime are of the same. They're all the same. And so I want to do all the same. The second thing I want is that there should be enough of these pairs. So that my law of large numbers thing works. And I want to have enough pairs. Whatever enough means. Enough pairs so that law of large numbers gives me concentration. If I have a small number of pairs, then I work in concentration, right? Then you work at it. So you need a lot of pairs to say that, okay, on average, and close. On average, it's an S prime has the same average, same data average. So if I need to strike a balance between these two. And now let me tell you how to do that. So it's actually it's a bit trivial. So maybe one of you can tell me also. So I have these two pairs of assets. Look at these numbers. Now, okay, now I want to generate pairs so that there is a set of hypotheses restricted to SS prime remains the same. How can I do that? Well, I want to keep working with the same set of numbers, right? That's the only way I will be able to ensure that the hypothesis class remains the same. I have to work with the same quantum x. But I want to generate a lot of pairs. How can I do that? It's trivial, right? How many pairs can you generate from these points? I have 2 points with me, right? I have 8 points in my hand. I know that if I just generate pairs from these 8 points, my hypothesis class will remain the same because I'm working with the same 10 points. So how many pairs can I generate from these 8 points? Something like 8, yeah, some exponential in 8 and 4, right? So 8C4 kind of stuff, roughly. But here I do something a bit simpler. I won't even do that one. What I will do is that I will look at all possible swappings of I and I prime. So I will maybe here is I and here is I prime. So I may swap these two or I may not. So I may do a 6, 10 here. Maybe for next I make another choice. Maybe I swap these two. I got 2, 3 here. Maybe for the next guy I don't swap. Or whatever it is. I keep it here. For the next one, maybe I also don't swap. Keep it 7 and 8. So this way, I will generate how many rows? For every pair I and I prime, I choose whether to swap or not. And I generate any row. 2 to the power 4 rows here. Generate 2 to the power m rows here. So generate 2 to the m rows, which is exponentially many rows, lot of rows. So hopefully good enough to get concentration. But still not so much that my h gets, so that my restriction of h to the set gets destroyed. Because at the same points have the same restriction, so the same h appears in the restriction of each of these pairs. But there's still a lot of pairs that I can still get concentration. And that's it. So now I'll say, okay, over these 2 to the m rows of this table. Now this is a finite number. Over these 2 to the m rows, I'm looking at some tau h 8 different hypotheses. Let's fix them. They're not fixed because at the same point. So the same hypotheses. So I have some tau h 8 different hypotheses. Yeah, h1, h3 till h tau h 8. Now these are fixed numbers, fixed hypotheses, not infinite anymore. And now I say that, okay, for each of these HIs, this average is small, because we managed to put so many of them that log large numbers is irrational. And I still only have small number of guys to look at, so I'm tooling and bound. Probability of things going wrong in any column is small. Only small number of guys to look at, so over probability is also small. So everything works. So that's it. Yeah, so that's how we make this wrong argument. So we'll do it formally and then finish things off. So it's just, yeah, I just write formally now, whatever I said. Yeah, so okay, great. So remember, we're looking at supremum over the image of the difference. 1 over m. From 1 to m L of h loss of h with respect to so in the book they call the sample as Zi. So Zi is SMI. So instead of writing SMI every time, I just write Zi now. Loss of h for Zi minus loss of h for the Zi prime. This is what we care about for any variance is okay, this is what we care about. And now remember our goal is to bound the expectation of this over S prime. Yeah. And now we will do this. Now I'll do this trick. Instead of looking at the overall expectation, I will say instead that okay. So you say that is the same as okay. So you take the average over S prime, but now you look at these two and these two and sample sequences. How do you generate them? You say that okay, I'll take expectation over these random choices. Remember, for every I can make a random choice as to whether to switch these two or not to switch these two. So let me indicate that random choice by some what's called another random variable. So this is the random variable sigma I, which is plus 1 minus 1 with probability half. So this variable is plus 1, then I don't switch. It was minus 1, then I switch. So after taking average over S prime, I first also take an average inside over the choice of these random variables. So this is sigma 1 to sigma m. Where sigma I is this distribution 1 over m. Sigma I so yeah. So yes, sigma is 1, they did not switch, sigma is -1, then they switched. And the whole trick is to say that this average and this average are actually the same. So why is it the same? Can someone tell me? So it's not what we just did, right? It's the same thing. I mean, it's written in a fancy way, but it's really the same thing. So what's going on here?
So there is a soup over soup Asian.
Oh yeah, sorry. Yeah. So. Anyway, so yeah, so why are these averages the same? Someone tell me.
So because if I swap these two expectations, then regardless of sigma 1 to sigma n, expectation of S dash of this thing, that is soup h in a script h 1 over n summation sigma I times that difference, that is going to be same for all this sigma 1 to sigma n, whatever sign I put to them.
Sorry.
So I'm saying that for every such same length string sigma 1 to sigma n,
Yeah.
expectation of S dash sample from Dm, that empirical mean weighted with sigma i's, that is going to be same.
Now, okay. I see what you're saying. Yeah, indeed, exactly right. So the point is that switching these two, whether I switch these two or not. Okay, so yeah, so here I have 10 and 6, right? Okay, so the point is that no, I think maybe let me say I don't know this is what you said, but let me say my reason. Then you can. So the point is that yeah. So when I'm taking average here, I'm taking average over every pair as well. In that every pair, these switchings are also accounted for. So when every pair appears here, all kinds of every switching also appears here. Right? So if I just do an extra switching after sampling the pair, that does not destroy my probabilities. Because anything is this switching is going to appear in this S prime. So all I'm doing is that instead of taking instead of just averaging over all S primes, after sampling S prime, I also do a switching. So that's really what we are saying. So the probability of getting a particular S prime here is not affected. Okay, this is more wizardry. You can just think of this. Okay, this is really all the same. So maybe it's not more than okay, I just look at these European rows and I'm just taking the average over those European rows. So this internal expectation here, this thing here is just the average over European rows. That's all it is. And I sampled n random variables, each telling me if I should switch I and I prime or not. And that generates 2 to the n rows for each possible sampling of x sigma. And I take the average over these 2 to the n rows. And then I take a bigger average over the choice of the first one. So that's it. So you don't know too much about etc. But totally that's it. Great. And now we are in good shape because this is going to be small. Phi is going to be small. Concentration, right? So see, now I don't care about distribution T anymore. Now I just have in my hand these numbers. So I have LXZ1 to LXZN, right? Okay, let me just write this difference. So let me call this number as some let's call it some beta. So I have a bunch of these betas. So the bunch of betas. So I really have this solution sigma I beta I. And sigma I is a plus minus 1. Right? So if I have a bunch of fixed betas with me, remember betas are not fixed things because I'm just looking at the internal expectation. Inside, the S and S prime are fixed. Okay? Here, when to the end rows, these numbers are all fixed. The only thing which changes is whether I switch or I don't switch. Average is only over that. So if I switch, then beta I becomes minus beta I. If I don't switch, it remains beta I. Right? So yeah, that's basically all that's going on. So now, okay, so now I can just use concentration to say that for a given h, with high probability, the absolute value of this average will be small. So now let's say that now is this now this figure hopefully. Okay, let's finish that now. So okay, so yeah, so let me call theta h as a standard variable. Theta h is 1 over m summation to m sigma I, then this quantity sigma I times beta I. Beta I was remember this difference, and yeah, and now I use Huptake's inequality. What does Huptake tell me? So Huptake tells me from last time that probability that this average, the absolute value of this average is bigger than any row, is smaller than 2 e to the minus 2m row square. And yeah, this is because why? Because these beta is at plus minus 1. Why is the sun because we're dealing with binary classification. Okay, so maybe this is 0, this is 1, or this 1 is 0. So beta is at plus 1. Is it plus minus 1?
It can also be 0.
Oh yeah, so is it interval? Yeah, so then you use Huptake's inequality. Yeah, so get concentration, so there's a chance that this average is high bigger than rho is very small. Yeah, its exponential is smaller than in m rho square. Yeah, so it is to be implementation again. It is on the board. So average of effort of theta is 0, right? This is 0 because sigma is up plus minus 1 with probability half. So average is 0, and I have n of these guys. So yeah, so now I use log large numbers. So chance that it's bigger than rho will be exponentially smaller than rho square. And
I mean, these are not identically distributed, right? These are just independent.
yeah, but it still works. Yeah. Okay, so I should not say all anymore, but yeah. How do you think about it? Okay, anyway. So great. So okay, so you have that, and yeah. So therefore, now I can use union bound. I can use union bound because now this equilibrium is not necessarily over all h, but only over those tau h of m pairs, or tau of 2 m pairs. So by union bound. Okay, so by the way, I can just put h in HC now, where C is SS prime. Yeah, I mean, C is the samples in SS prime, and S union S prime. Yeah, so I just look at h in HC now because yeah, everything else is the same. So every h in H is one of HC for as long as if it's only care about these losses, then I just look at HC. And now, now finally the ghost function comes in. So probability that Now this quantity here, theta h, is bigger than rho. Mod of theta h. No, so sorry, max h in h mod of theta h bigger than rho is smaller than that thing. 2 times tau h of Coulomb times e to the minus 2m. Okay. Why closer to m? Because at max you can have 2m different values. So it is a given bound of this over 2mx. Probability that this is bigger than rho is smaller than this. And yeah, and now we can do some some manipulation of this. So which I will not do it in class. So yeah, so you can manipulate this a little bit and get that. So this then implies is some algebra, which I have not write, that the expectation of max h theta h is now at most 4 plus log tau h of 2m by square root of m. Okay. So yeah, so I'm not sure how this works, but this really is not so hard. So that point is that the chance that this is very big is very small. So on average, this is going to be small. Yeah. So this you can do on your own. You can look at the book. So, yeah, there's no intuition here, just calculation. I want to yeah. And yeah, that's it, right? This all I have to show. Yeah, so I mean, okay, so we show that for every order as an S prime, this thing is small, and so the expectation will also be. By the way, this is SC here, but yeah, but SC is the same as H. So doesn't really matter. So that's it. Long proof, but hopefully. Yeah. So don't worry too much about this algebra, that's not so important. The important thing really is 3 ideas. First idea is that somebody have to use combination. You have to say that, okay, you have to suppose that if I average is small, then the high probability, my actual number is small by concentration. So somebody have to use that. And the second is that you have to somehow bring the growth function in. You have to limit the number of h's for which you use union bound. For that, you have to say somehow that even though I can have a lot of h's, I can have infinite h's, but I can somehow focus my attention on only a small number of different h's. How do I do that? I have to somehow reduce my problem from looking at the entire distribution to only samples. So that was something which we did here. Go from D and S to S and S prime. That is the second idea. The third final idea is to somehow be able to look at the same edges, the same tau h of 2m edges across my different samples. So remember the problem was that different SS primes can have different tau h of 2m edges. So I cannot really do an averaging. So that's where this trick came in. I fixed some SS prime. After fixing them, I said that okay, let me generate 2 to 3m different SS prime pairs and average over only those, not over everything. And somehow, because we generate these pairs, we generate a lot of pairs, I can still get concentration. So it's not a balance between, between needing a lot of different SS prime for concentration and and having different towers of 2 and 2. I was able to get around both of them. And finally, finally it's just okay, inequality, union bound, stuff is then everything comes together. Okay, I think people are very tired now. So, thanks for